All right. So we want to start this off, and we will we are going to talk about the network layer. So again, welcome to this class. So the network layer, as we all know, this is the this is layer 3 of the OSI layer. We have been talking about, we did talk about layer 1, which is the physical layer, and we talked about the network media within the physical layer, and the 3 types of network media were copper, fiber optic, and wireless. All right. Then we went to the data link layer, which is layer 2 of the OSI, and within the data link layer, we talked about the addressing types, where we talked about the binary addressing system, the decimal addressing system, and the hexadecimal addressing system. We also talked about the data link layer and the different subdivisions of the data link layer, the LLC, the logical link control sublayer, and the MAC sublayer, the media access control. And then, of course, we talked about switching, Ethernet switching yesterday. And in Ethernet switching, we did talk about the MAC address, functions of the MAC address, the structure of the MAC address, how the MAC address is formed, and we talked about the switch, and we talked about the MAC address table of the switch. That is the most important table that the switch has. You know, a switch without a MAC address table is not a switch. Okay. And so today we now want to talk about the network layer. And like I mentioned to you, the network layer is where we find the IP address. So expect us today to talk about IP address, IP version 4 and IP version 6. Expect us today to also talk about the router and the routing table. All right. We saw the table in the switch, and now we are talking about the table in the router, which is the routing table. So throughout this chapter here, we'll explain how network layer uses IP protocols, how network layer uses IP protocols for reliable communications. And then, of course, please specifically, we talk about IP version 4, and then we talk about IP version 6 packets. Remember, the packet is the PDU at layer 3. The PDU as layer 3, we have the packet. So we look at the differences between the packet for IPv4 and the one for IPv6, and why IPv6 is efficient than IPv4, why IPv6 is more secure packet. Remember, when we talked about the frame, inside the frame we have the packet, yet inside the packet we have the segment, and inside the segment is what carries the data traffic we are moving, the voice, the video, the emails we send, the web pages we read from the web server, the YouTube videos that we watch, the softwares we download. Everything is contained normally within the packet. So today we learn about the PDU at layer 3, which is called the packet, the IP packet, as in 2 versions, version 4 and version 6. As usual, we explain how network devices use routing tables to direct packet to a destination network, and then the functions and fields within the routing table of a router. So let's get started, ladies and gentlemen. And to start us off, the network layer basically provides or allow end devices to exchange data. Very important. And 2 versions of it, version 4 and version 6. And these are the major network layer communication protocols found there. So they perform the following functions. They perform addressing of end devices. They perform, so basically addressing of end devices, assignment of IP addresses to the end devices, making the devices to be identified within the internet protocol. within the IP protocol. All right. Then they also perform encapsulation. This is where, of course, the segment is encapsulated to form the IP packet. All right. They perform routing, and the word routing basically means the transfer of a packet from one device to the other, or from a network to the internet. You know, the internet is also a network. That is routing. And finally, they also do the encapsulation. Okay, when the packet has to be de-encapsulated to expose the segment, that is the encapsulation. So there's a couple of those major functions that are performed by the network layer. Now, talking about the IP encapsulation, it is important to note that here is where the transport layer segment, the segment is normally encapsulated to form the packet, which means the segment is found right inside the packet. Okay. We did learn that MAC addresses change from network to network, but IP addresses does not change from any source to any destination. Now, this is very important, except something we call NAT, network address translation, which, of course, we will talk about later on. So you can see here, this is a segment which contains data in it. Is actually encapsulated to form what is called the IP packet or the IP header. Now we look at the fields a little bit sooner now. Let's talk about the three major characteristics or features of the IP protocol. Features or characteristics of the IP protocol. There are only three. The first one is it is connectionless. Number two, it has what is called best effort. And number three, it's media independent. I'll start from simple to complex. I'll start with the last one, media independent. So media independent means that this IP protocol, it does not choose which type of media will be used. We know that we have three types of network media. We have fiber optic, we have wireless, and we have copper. So the IP protocol does not choose which of those three types of media to use. That's why we say it is media independent. Best effort. Now, talking about best effort, when you talk about best effort, basically, the IP protocol, it does not guarantee the delivery of the packets, okay, from one device, from one source to another destination. So delivery is not guaranteed of the packet. So then someone will ask, how come the packets get delivered anyway? It's because that the delivery is always guaranteed by the next layer, which is the transport layer. It is the transport layer that ensures that delivery is guaranteed, okay? And so best effort means, delivery will just happen for the sake of it all, but it's not guarantee. It's not a guarantee that you send an email, it will always reach a destination. But that function is done by another layer, which is, of course, the transport layer. Connectionless. Talking about connectionless, again, when your device is sending a packet through the IP protocol, the IP protocol, which is found within the network layer, it does not establish any connection with the destination device before the message is delivered. So before the packet is delivered, the source device does not establish any prior communication with the destination device. Again, that function, which brings a lot of reliability, is always ensured with the next layer. It's always ensured. Like, let me give you a very good example of connectionless. You want to send up, let's say you're selling some products, like let's say shoes. You're selling some shoes online, okay? And you have all your presence is on Facebook and on WhatsApp status and on Instagram. So what happens is that you are in Nairobi, capital city of Kenya, and you want to send these shoes, let's say, to someone in another city in Kenya, Kisumu, and so the person in Kisumu has already seen your shoes online and they've reached out to you. So when they reach out to you, you talk to them and you tell them you're gonna need to pay this, or we will deliver first and then you pay. So what happens is that you are able to know each other before you send the parcel. You guys are able to establish a rapport. You're able to exchange contacts, and so that you're not talking to a robot. You're able to talk and you can tell them, I can actually deliver that to you, and don't worry about payment. You are going to make the payments upon delivery. So the prior relationship you make before you deliver the packet, we say that that is the opposite of connectionless. That is the opposite of connectionless, and it is called connection oriented. So IP, now the two devices do not establish that prior communication before the data is sent. That function, again, it is done at the transport layer. So that's why we say IP is connectionless. It does not establish any prior communication with the destination device. That's very, very important. So these are the three characteristics of the IP protocol: connectionless, not establishing any prior relationship with the destination device. Best effort, delivery is not guaranteed the packet because the guarantee is actually ensured by the next layer, which is the transport layer. Media independent, the IP protocol does not choose a specific type of media. It can actually use any of them, so on and so forth. So let's talk about the IPv4 packet. And of course, we are going to see how to compare it with the IP version 6 packet. So it's important to note that this packet normally contains a binary. It's actually normally indicated this in a binary, and that is on the version part. If you guys can remember very well, if we can remember that, the thing is, I taught you how to write during the transitions, the translation from hexadecimal to decimal and to binary. For example, I told you to use the first multiples of 2. We have 2 power 0, 2 power 1, 2 power 2, 2 power 3. So 8421. 8421. If you take 8421, let's say you take 6, you take, let's take 4. If you take number 4 and you write it in binary using 8421, so you ask yourself, among the numbers 8421, which numbers add up to 4? It's obviously it is 4. So you put a 1 under 4, which means, and you put a 0 under the other one. So under 8 will have a 0, under 4 will have a 1, and then under 2 and 1 will have 0, 0. So the binary, 4 into binary will be 0, 1, 0, 0. So when you look at this packet under this packet, you look at it under Wireshark, you'll always see the version here written in form of binary 0100. That's very, very important. Now, apart from the version here, which is one of the fields within the IPv4, there are several other fields here that are in IPv4, and you realize that we have given them different colors. Okay, we have the purple color. The reason why it is given the purple color is that when we will be comparing version 6 and version 4, the purple colors will remain the same. You'll see version, you'll see source IP here, and the destination IP here. Where the source IP is just the IP address of the source device, and the destination IP is the IP address of the destination device. Okay. And there's other fields like the fields that are in gray here. Those fields that you see in form of gray, those are fields that are all going to be removed. When you look at IPv6, it is going to, it is not going to have the fields in gray here, including the internet header, total length, identification, flag, fragment offset, header checksum. All those ones are going to be omitted in IPv6. And the fact that so many of those fields are going to be omitted tells you that IPv6 packet is very light, and that's why it is faster than IPv4. The IPv6 is much faster than IPv4 because it carries very, very few fields. All right. There's a part called the DS. DS basically means differentiated services. So DS, DSCP, and the ECN, this is the part that does quality of service. It is a part that does quality of service. And we did talk about quality of service, whereby quality of service helps in giving priority to some traffic than others. Like the voice traffic and the live video traffic is always given more priority on the network than the others. Then look at the time to leave packet. This is very, very important, the TTL. The TTL, by the way, will get a different name. That's why it is given color green here. In IPv6, it will have a different color. Sorry, a different name. It will have a different name. The same as protocol is given blue color here. It will also have a different name. Time to leave. Let me talk about time to leave. So time to leave is the part of the packet which ensures that this packet can never go round and round the internet without reaching the destination. So if every packet that leaves a source, it is given a specific TTL value. Basically, that is just a value. And as a packet moves from one device to the next, one router to the next router, that TTL value is reduced by 1. It moves to the next router, the TTL value is reduced by 1. It moves to the next router, it is reduced by 1. If that number is reduced up to 0 before it reaches the destination device, then the packet will be dropped. And that is going to prevent the packet from going round and round the internet without ever reaching the destination. So that is very, very important thing for us to note. Okay. So time to leave, very, very important, and it will give a different name. Protocol is actually the next layer protocol. You know, the next layer is the transport layer, where we have TCP or UDP. So that is the protocol layer. Of course, in IPv4, header checksum is used for checking of errors. Total length is actually the total length of the packet. The flags and the fragment offset, those are just different fields within this packet. Now, they are not very significant for our study now. Now, of course, like I had mentioned to you here, the version will always be written in form of binary 0100. The differentiated service is for quality of service. Header checksum is for checking of errors here or any corrupt packets. Time to leave is a hope when it becomes 0, then the router will actually discard that packet, and that packet will be removed from the network because the TTL value, time to leave value, was decremented to 0. The protocol is actually the next level protocol like TCP, UDP, ICMP, so on and so forth. Source and the destination IPs are actually just the source IP addresses, which are 32-bit addresses as we had learned before. Now, let's look at IPv6 packet. And before we talk about its packet, we want to talk about why are we moving to IPv6 from IPv4. I know I have talked about this before, but it's no harm, mention this again. So the IPv4 addresses have already been depleted. That is very important information. The whole world has run out of IP version 4 addresses. The whole world has run out of IP version 4 addresses, all the 5 regional internet registries and the 5 continents. IPv4 lacks what is called end-to-end connectivity. How so? Because we have exhausted all the available public IPv4 addresses, currently every network uses what is called private addressing and combined with what is called network address translation. And this makes sure that when you're in one network, you can never ping a private IP in another network. Let me explain that to you guys so that you get to know. I'm going to open my command prompt here. And when I open my command prompt, I want to look at my IP address here. Say IP big space / okay. Now My IP version 4 address, which is my private address, is actually here 192.0.108.0.108. That's my private IPv4 address. Okay. By the way, any address that starts with 192.168 or 172.16 or 10 dot something, those three groups, 192.168, 172.16, and 172.16 can, the second octet can range from 16 to 31. So 172.16.17.18 all the way to 31. And the last one is 10 dot something. Those ones are called private IP addresses. Now, that is my private IP address. That private address cannot be used to connect to the internet. But you can ask me, how come I'm using my computer now to connect to the internet, and yet I'm having a private IP address? It's because of this. It's because right now, on my browser, I just need to type my IP address.com. If you type my IP address.com on your browser and I press enter, the next thing you're going to see here, you'll see everyone in my network. You'll see what is called my public IP address. This is the address provided by ISP 102.220.231.20 something there. Okay. So this is my public IP address. This is the IP address that is currently being used. Everyone in my network. If I have 10 people in my network, in my Wi-Fi network right now, all of them, each of them has their own private IPs. But because the private IPs cannot be used to connect to the internet, my network implements what is called network address translation, in short NAT. And NAT can be able to translate all our private IPs into this one public IP. All our private IPs into a single public IPs. The reason why, even if we are 500 in my network, we can share this one public IP. It's actually because the world has run out of these public IP addresses. The world has run out of the public IP addresses, and we currently are just sharing public IP addresses, but that is a temporary solution. That is actually a temporary solution that is not going to last for long. That is not going to last for long. Now, it's important to note that, and we will have a whole chapter where we will be talking about network address translation. So that therefore means that if in your own private network, you can never ping the IP address of private IP of someone in another network. Okay? And it's because of the use of NAT. And NAT has had some complexities. NAT has had some complexity. And that's why we are moving away from IP version 6. Now, IPv6 was developed by IETF, the Internet Engineering Task Force, and IPv6 has overcome most of those limitations that we have with IPv4. Okay, and therefore some of the improvements that we have in IPv4 in IPv6 include: we have an increased address space. IPv6 had 128 bits, while IPv4 was only having 32 bits. Number one. And I told you that IPv4 were 4.3 billion, IPv6 were 340 and decillion. Actually over 340 and decillion. In a short while, I'm going to show you what undecillion is. Then, of course, IPv6 has what is called improved packet handling, because IPv6, unlike IPv4, has very few fields. It has very, very few fields, and that gives it time to be able to do what? To handle the packets. Now, IPv6 has eliminated the need for NAT. The need of sharing one public IP for 1,000 or for 500 people is no longer there, because for IPv6, we have a huge number of addresses, so that there's no need for private in mapping one private to public, so on and so forth. Let me show you what undecillion is. So this is what undecillion is, ladies and gentlemen. Let me just remove this here, and let me zoom in so that you can be able to see what an undecillion is. So if you can see my diagram well, all of us know that 1000 normally is 10 raised to power 3. So which means 1000 has 3 zeros. A million has 6 zeros. Okay. A billion has 9 zeros. Okay. A trillion has 12 zeros. A quadrillion has 15 zeros. A quintillion has 18 zeros. A sextillion has 21 zeros. Septillion has 24 zeros. 1 octillion has 27 zeros. A nonillion is a number with 30 zeros. Then we have what's called decillion. It's a number with 33 zeros. And then we have our number down here. And decillion. And decillion, where IPv6 addresses are, is actually a number with 36 zeros. So 1 with 36 zeros, we call that an decillion. So normally, we actually do have 340 with 36 zeros number of IPv6 addresses. This is a very huge number of addresses, ladies and gentlemen. And like I was telling, someone actually jokingly says that an IP version 6 address, an IP version 6 address, an IP version 6 address, there are so many such that if you can be able to any other thing. Yeah, if you can be able to count the number of sand grains in all the continents of the world, if you can be able to count all the sand grains in all the continents of the world, then that is the number of IPv6 addresses that you do have. So there are 340, and decillion is actually above that number, and you know, they are huge. Look at the IPv4 are only 4 billion with 9 zeros. IPv6 are 340 and decillion. So that basically tells you that there are so many addresses that we have there. Now look at the packet header for IPv6. Very light, and it's very free. All right. So you can see the version still remains here. Okay. The source IP and destination IP remain as purple. Traffic class, this is what we were calling time to live. Traffic class. No. I'm actually wrong. Traffic class was actually the part that we are having for differentiated services. Differentiated services for quality of service is what we call traffic class. The name has changed. Hop limit was our time to live. Hop limit was the time to live. Next header was actually the protocol. The next protocol layer can be a TCP or UDP. The next header is like the protocol in IPv4. Hop limit, like I said, is the time to live. Payload length is like the total length of the packet. Okay. The only field that has been introduced here after all the others were removed is what's called the flow label. What's called the flow label. So again, the function of the flow label is basically informing the device to handle any identical flow labels the same way. But the rest are the same. Version, since this is version 6, you write 6 in binary and you'll get 0, 1, 1, 6. So 6 is actually 4 and 2. So you put 1 under 4 and 1 under 2. And you put 0 under 8 and 0 under 1. So you have 0, 1, 1. Traffic class is the same as the DS, differentiated services for quality of service. Payload length, this is like the total length of the packet. Next header is the next level protocol, either ICMP, TCP, or UDP. hop limit was like a TTL value, which as it reduces when it reduces to 0, then the packet will actually be dropped by the router. And 128 bit source IPv6 address and destination IPv6 address are actually represented down here. So these are the differences between the fields for IP version 4 and the fields for IP version 6. Now, a few special things about IPv6 packet header. We always say that the IPv6 packet header is a bit secure, and it is faster. It is because it contains something called the EH, the extension header, which provides more information, including security, mobility support. So much faster in terms of mobility, and the security of it here. Of course, fragmentation is also there. So this is why the IPv6 packet header is there. And there's a disclaimer here. Routers do not fragment IP packets. Okay, routers for IPv6 do not normally fragment the IP version 6 packets. Now, let's now talk about routing, because routing happens at layer 3, switching happens in layer 2. So to talk about routing here, it is important that we look at packet forwarding decisions. And to do this, we need to note that messages are always created at the source device, and that is end devices: laptop, tablet, PC, server. Normally messages are created in them. And that's why end devices, just like routers, also have a routing table. And that is one of the things that you'll learn in this course, that a computer has a lot of similarity with the router, unlike a switch. And sometimes a computer and a PC or and a laptop are considered as same devices, and you can actually use crossover cable to connect them as same devices. Very, very important. And if you did one of the assignments that I left you some time back, you must have seen that. Okay. Now, a message from a PC can be sent in 3 ways. And of course, it's a packet. So a packet can be sent, a PC can send a message or a packet to itself. And if you want to do that, you just need to ping this particular IP address, 127.0.0.1. This is called a loopback IP address. Every time you ping this IP, it's like the device is actually pinging itself. If you ping your PC, ping this IP, it does not belong to a specific device. So it's like the device is pinging itself. So loopback IP 127.0.0.1 in IPv4, :1 in IPv6. Where :1, of course, this is a way of shortening of IPv6 addresses. I will be able to teach you what : is. : is actually representing zeros. So apart from sending a packet to itself, a PC can send a packet to a device within the same network. That is to a local host within the same network, or a PC can send a packet to a device in a remote network. So that's what we are actually trying to demonstrate here. This PC here, if you ping 127.0.0.1, it's like it is pinging itself. If you ping a PC on the same network, this is the same network here, then it can send a packet to a device within the same network, but it can also ping or send a packet to a device outside in another network. By the way, how do you know that this network is different from this network? Simple. A router. The only device which can connect one network to another. In fact, every interface of a router connects to a different network. Every interface of a router connects to a different network. So long as you see a router and you see cables connecting from different interfaces of that router, That is how you can be able to know the number of networks here. So for this, our particular topology here, we do have 2 networks here, simply because we have router R1, and router R1 is connected to this server, a remote server, to the internet, and R1 is also connected to one. We don't count the switch when counting networks, by the way, because a switch is always found within one network, within a network. A switch cannot connect one network at another. It is the router that connects one network at another. So when you see a switch, even if there are 1 million switches connected together, the whole of that will be called one network. So that is important for you guys to know. One of the activities you'll always be required to know is to count the number of networks in a network diagram, in a topology. Look at the router. Ask yourself, how many connections are there on the router? There are only 2. This one and this one here. So these ones are 2 networks. But don't worry, we'll talk more about that later on. We have this that we call default gateway. A default gateway, by the way, I told you that the device found at network layer is a router, but there's another special type of switch, which is also at layer 3. Actually, we call it a layer 3 switch, or we call it a multi-layered switch. The reason why we call it a multi-layered switch is because it can work at both layer 3 as a router, and it can also work at layer 2 as a switch. And it is very expensive, because if you buy a layer 3 switch, it's like you have both the switch and router put together in one device, and that's why it's expensive. So a default gateway is actually any router or a layer 3 switch is called a default gateway. And the IP address assigned to that default gateway is what is called the default gateway address. Is what is called the default gateway address. And that's why every computer must have an IP address of the default gateway for that computer to access devices outside of the network. Okay? That device must always must have a default gateway IP address. And you can see that even in my network here. Look at my IP addressing here. My IP address is here, 192.168.0.108, but I must have a default gateway, which is here. A network without a default gateway cannot be able to access beyond the network, beyond the LAN. That means it cannot be able to access services within the internet or any other network. So the default gateway, very important. A PC or a laptop or a mobile phone without a default gateway cannot access the rest outside of the LAN. And that's why any PC in the network, its IP address must be on the same network with the default gateway. And that's why we are saying the default gateway must have an IP address in the same range as the rest of the local area network devices, because it is the only connection between that network and another network. So it accepts data from the LAN and it can forward it to another LAN or even to the internet. Okay? And that means it can route traffic to the other networks. And that's why we have the word routing, the process of sending a packet from one network to another network. That can only be done by a default gateway. And you have said a default gateway is either a router or a layer 3 switch. Excuse me. Now, look at this. If a device has no default gateway, or it has incorrect or bad default gateway, then it means the traffic will never leave the LAN. That means you'll never browse the internet. Okay? Now, like I've mentioned, every router must always have a default gateway. Okay? And so default gateway can be obtained, of course, through DHCP, or it can be manually configured. Okay? So for any device that wants to send traffic outside of the network, you must have a default gateway. You can still send traffic within your own local area network without using the default gateway, but to access devices or other places outside of your network, let's say this is a network here. Maybe there are these PCs here. This PC can communicate with this PC, PC2 here, PC1 can communicate with PC2 without the services of a router. But if PC1 wants to browse a server, a web server, Google, YouTube, Facebook, Twitter, within the internet, then it must have the IP address of this router here, which is going to be the default gateway of all the devices within this particular network. Okay. Now, I need to note at this point, because this is something that will come. Every network, like the whole of this is a network, must have its network address, and the network address is like the name of this, the whole of this network. So the whole of this network is 192.168.10.0. This is the whole of this network. And note this, since this is like the name of this network, /24, where /24 is what we call a subnet mask. So the network address cannot be assigned to any of these devices. It's like the mother of all these devices. To start assigning, we must start assigning from 10.1, whereby in most cases, the router interface is always given the first IP, but it is not a rule. It is just, recommended. Sometimes some devices are given the last IP. I will talk to you about first and last in soon. So you can see, when you see here .1, it means the IP address of this router interface is 192.168.10.1. So replace where the 0 is, put 1. This PC here, its IP is 192.168.10.10. And the IP address of PC2 is 192.168.10.15. So please note, every time you see the dot here, .10, you replace the 0 with that .1, and that is actually the IP address of each and every device here, while .0 is the network address of the whole of this network. We in chapter 11 and chapter 12, I will give you a wealth of knowledge about that particular activity. Now, like I told you that PC has some similarities with a router. Just like a router has a routing table, a PC also has a routing table. To see the routing table in a PC, you can use either of these two commands. Either just type route print, or you type netstart space -r. Netstart space -r, you'll be able to see the routing table of your PC. Netstart does not have an R here. Netstart, the start does not have an R. So netstart, like the network statistics, okay? Netstart space -r, route print. So either of them will give you the same output right here, and you'll be able to see the IPv4 routing table and also the IPv6 routing table. Both of them will actually be listed together, the interface list. Okay. Now let's look at routing within the router. And this is where I want to spend some little bit of time here. I'll talk about some bit of encapsulation, but before I do that, I want you guys to see something. I want to ask you a question, and I will expect you guys to just to respond to that. Okay. Let me ask a question here, guys. Okay. My question for you. Since I have taught you how to count the number of networks, how many networks can you see from this diagram? Look at the routers very well and pick in before you answer that. How many networks can you see here in this network diagram? Someone? Don't fear to make mistakes. Don't think, we are all here to learn. So every answer in an answer, every answer will make us to learn. Let me get, how many networks can you see in this diagram? Of course, you can see we have two routers, R1 and R2. We have a switch here, we have a switch here. We have PC2, we have PC2, we have internet here. So how many networks can you see? Just what you can see, not what you think. How many can you see?
Can say 2.
Okay. Okay. Let's get more answers.
3.
Someone can see 3. Okay, 3. So there's 2, there's 3. Any other person?
4.
All right, someone can see 4. So there's 2, there's 3, there's 4. Please don't be left behind. Tell us if you think someone has said your answer, just say it. We can also take statistics on, how many 2s did we have, how many 3s, how many 4s. Those who have not talked, please shout out your answer. How many networks can you see? Okay. Okay, 2, 3, 4. Okay, let's count it together. So first and foremost, let's look at R1. R1 has 2 connections. R1 has interface G0/0/0. The G means gigabit Ethernet. Gigabit Ethernet. So gigabit Ethernet 0/0/0 is the first interface of the router. So the whole of this is one network. It doesn't matter so long as there's no router here, so long as it is just a switch. Remember, a switch is transparent. You can as well remove this switch here and connect PC directly to the router. That will still be a network. The presence of the switch here just allows you, since if you have one interface G00, which you can still connect the PC directly to it. But if you have more than one PC, you have 20 PCs, you cannot connect all the 20 PCs to this router interface. What do? You bring a switch and connect it to that interface. Now, because a switch normally has very many interfaces, unlike a router has very few. So the switch, some switches have 24 ports, some have 48, some have up to 400, up to 1,000 ports, switches we use in data centers. Now the 2960 series switch has 26 ports actually. So if you can be able to connect the switch to the port, then now you'll have more ports to connect end devices here. It doesn't matter how many switches are here, so long as all those switches are connected together, they have PCs, but so long as they're joined to one router interface. So the whole of this is one network. And you can see here, the network name is 192.168.10.0. So that is 1. That's our network number 1. Then look at R2. Of course, R1 was having G00 and G001. This is gigabit Ethernet 0/0/1, which means R2 is already connected to R1 is connected to 2 networks. R1 is connected to network number 1, and R1 is also connected to this network here. Okay, so the whole of this is a network, and you can see its name is here, 209.165.200.224/30. Now, this is a special network here. The reason why I'm calling it special is because when you're in R1, we say R1 is connected to 2 networks. When you're in R2, R2 is now connected to also 3 networks, because R2 has this network here. R2 is also connected to the same network here. Can you see the same network that R1 is also connected to? So wherever 2 routers are joined by a network, that network is counted as 1. You don't count it as 2. Okay? So this network, even though R1 is connected to it and R2 is also connected to it, this network is 1. That's why look at this. This is 201.165.200.224. That is the network address. The R1 side of this same network is 200.225, and R2 side of the same network is 200.226. So this is counted as one network. Then, of course, we have already seen this is a third network. 10.1.1.0 is another network. And finally, so we have seen 2, and then we have seen 3. Then now we have R2 also connecting us to the internet here. So the link from R2 to the internet is also another network. So those who said 4, that was the correct answer. Those who said 2 and 3, you have learned why we don't have 2 networks and we don't have 3. We actually have 4 networks, one being shared between R1 and R2. There's a LAN for R1, another LAN on R2, and then there's a connection to the internet. We will get more topologies, and I want you to always know how to count the number of networks in your topology. That is very, very important. That is very, very important. Now, having talked about that, I'm required to remind you of encapsulation and de-encapsulation of packets. A packet is moving from PC1 all the way to PC2. Remember what I told you? Encapsulation. So the packet from PC1 arrives on R1 through G000. R1 has to de-encapsulate the packet. R1. First, the message is actually received in form of a frame. The frame is de-encapsulated to view the packet. The packet is actually going to be seen by R1. And you know the packet has source IP and destination IP, where the source IP will be for PC1, the destination IP will be for PC2. So R1 will look at the packet, check the destination IP, compare it with what is on the routing table, then de-encapsulate, of course, the frame to see the packet, examine the packet, searching for the best path on its routing table according to the destination IP. Once that is that, then R1 is actually going to re-encapsulate that frame, the packet with a new frame, and forward it to the next device R2. You know, when it is being sent as a frame, the frame is encapsulated into a bits before it can move on the media. You know, this is copper media. So along the copper media, it moves in form of bits of zeros and ones. When it gets to R2, R2 de-encapsulates the bits into a frame. The frame is de-encapsulated to view the packet. The packet, the destination IP on the packet is going to be used to examine the routing table to check, is it going to the internet or is it going to PC2? Once that happens, then R2 is going to re-encapsulate that packet using a new frame and re-encapsulate the frame into bits of zeros and ones, and it is forwarded to PC2, of course, passing through the switch. So it is important to checking even the process of encapsulation and re-encapsulation. And this is actually, what I want you to note is that what happens to the packet. R1 examines the destination IP address of the packet and searches for the best match. Where am I sending this packet? It will search for the best match in its IPv4 routing table. Then the routing table entry indicates this packet is to be forwarded to R2. Okay, so the packet will be saying that the destination should actually going to R2, and that is something we'll be checking. Of course, the routing table is here. The destination was actually 10.1.1. something, so it was 10.10. The packet was having 10.1.1.10, so it will be sent to this particular network here. It will be sent to this particular network here. It will be sent to this particular network here, which is by R2. We will look at the routing table in more in more details soon enough. The good news is that this concept will be repeating almost every now, time, and then. Now, listen to this. The routing table. There are three types of routes that we normally found within the routing table. There are three types of routes that we normally found within the routing table. We have what is called directly connected route. Directly connected routes. Now, a directly connected route is actually a route which is inserted in the routing table after you have configured an IP address on the router interface. Configure an IP address on the router interface and then activate that interface. Of course, I'll be showing you how to do that soon enough. Now, so to configure an IP address on a router interface, if you can be able to do that, which I will show you, of course, then the IP address is going to be entered or recorded within the routing table as a directly connected network. Now, to make more sense, guys, if there's anything I always want to do is to not just appear to be making sense, but to actually make sense. Now, let's look at here. And I'm going to need your concentration very closely here. A couple of minutes ago, we just counted the number of networks here. We say 1, 2, 3, and 4 networks. They went to the internet. Now, this is the point where I want to mention something very crucial for your networking experience and for your networking learning with me here. So the first thing I want to note is that the two networks which is directly attached to R1, this network and this network, they are directly attached to R1. These networks are called directly connected networks. And if you configure the IP address interface G00 with this IP address 192.168.10.1, and you also configure interface G001 with an IP address of 209.165.200.225, configure those two interfaces, and then activate them using a command no shutdown. Then those networks are going to be registered in the routing table as directly connected networks. So to identify directly connected networks, they're actually networks that are directly attached to the router. So R1 has two directly connected networks. R2 also has how many directly connected networks can someone see in R2? Let me get that answer from you guys. How many directly connected networks does R2 have? Someone?
Two.
Very good. Very good. R2. So did you say 2? Look at R2 well.
3.
How many directly attached? Very good. Should be 3, not 2, really. You can see the network going to here. It is a network connected to here. And there's the network going to the internet. Those are 3 directly attached. So these are 3 directly connected networks of R2, but R1 has only 2. Now, look at this. Look at this very keenly, friends. R1, so total number of networks here are 4. 4. R1 is directly connected to 2. R2 is directly connected to how many? To 3. Because of course they are sharing this one. Now, if you have 4 networks here in total, and R1 is directly connected to 2 of them, how many are remaining? 2 more. Out of the total 4, R1 is directly connected to 2 of them, which therefore means that there exist 2 networks which are not directly connected to R1. Okay? There exist 2 networks which are not directly connected to R1. Those networks, even though they are not directly connected to R1, but they are directly connected to R2. They are directly connected to R2. How do we call networks that are not directly connected to a router? Network to the internet and network to remote network are not directly connected to R1. R1 calls them remote networks. R1 calls them remote networks. Okay? Look at R2. R2 has 3 directly connected networks. Out of the total 4, R2 is directly connected to 3 of them, which means there's one network which is not directly attached to R2. That network is here. That network is not directly attached to R2. It is only directly attached to R1. So if you are in R2, any network that is not directly attached to R2 is also called the remote network for R2. The remote network for R2. So R2 has this network as a remote network, but R1 has these two networks as remote networks. Very important to note that. Why am I saying that? I'm saying that because the major objective of every router, and the reason why we are able to communicate to devices all over the internet. You're able to browse a web server in South Africa, a web server in Oxford in the UK, and Google servers in the US, or netaka.com servers found in San Jose in the US. It's because all routers in the world are interconnected. That's why we call the world a global village, because of the internet. So the word internet comes from the word interconnection of networks. Internet is interconnection of several networks. So it is the router which is at the central of the working of the internet, because it is the routers we have all over the world that interconnects one network and another network. Okay? And that therefore means that routers are very important in a network. Now, how is it that a router in my network here is able to communicate with the network where you are right now? It's because my router must know how to reach the router that you are connected to in your network. Whether you are in the UK, whether you are in the US, whether you're in Tanzania, whether you are in Kenya, Kisumu, Mombasa, Nakuru, even within Nairobi city here, your router must know how to reach my router, and my router must know how to reach your router. So the whole process of another router knowing to reach another router is actually what we call routing. Okay? And so each router must know how to reach all the remote networks, leave alone the directly connected networks. The directly connected networks, those ones will be learned so long as the router has actually done what? Been configured an IP address. So every router must know how to reach its remote networks. And you know, there are so many remote networks in the world. Now, there are only two ways of learning remote networks. There are only two ways of learning remote networks, which means for R1 here, to learn these remote networks, one is to the internet and one is to this network here. R1 has two ways. Way number one is called static routing. Static routing. Static routing is actually manual routing. Why do we call it static routing? Is because to learn the remote network, you, the network administrator, you must know all the remote networks and manually add them in your router. Look at that tedious job. You, the network admin, must know the remote networks and manually keep on adding them in your router. Number two, if there are so many for you to add in your router, then you can do it automatically, which is called dynamic routing protocols. You can use a dynamic routing protocols, one of which is OSPF, Open Shortest Path First, EIGRP, Enhanced Interior Gateway Routing Protocols, BGP, Border Gateway Protocols, ISIS, Intermediary System to Intermediary System, RIP, Routing Information Protocol. So you either decide to do manually, and you know, manually, everything done manual always has repercussions, because the more work increases, the harder it becomes to do manually. Or you can do it automatically by configuring a dynamic routing protocol. You do it dynamically. Now, it is important to note the following, that towards the end of the next module, which is CCNA 2, we are going to talk about routing. Static routing, we will start with it, then we go on to dynamic routing. Now look at this, look at this. What if you want to do it manually? You want to add all the remote networks in the world manually in your routing table, but you can't, the router cannot take all of them. What are you going to do? We have something called a default route. A default route is a special type of route, which I always call it a universal route, because when you configure a default route in your router, it's like you configure a route that can reach all the remote networks in your world, in the world. You configure one route that can reach all the remote networks. It's like you're adding a route for reaching all the remote networks within the internet. We will talk about default routing, and we'll talk about remote network, static routing and dynamic routing protocols. That time will come, and I will do it to the best of my ability, just to make you guys to be able to understand. Anyway, so we want to get this done now. It is important, of course, I've already talked about static routing and all that, where you manually add the routes within the routing table. And there's a sample command here. Of course, that we will cover much later on. You say IP route, put the remote network address, put its subnet mask, then put something called next hop IP, which of course we will learn later on. If I teach you now, of course, you'll forget. So I don't want you to teach you that now. I will teach you that when the right time comes. For the dynamic routing protocols, how do they work? Very important. For dynamic routing protocols, this is how they actually work. Let's say there's R1 and R2 here. R1 has two directly connected networks, this one and this one. R2 also has two directly connected networks, this one and the one they are sharing here. For R1, this is a remote network for R1, and this one here is a remote network for R2, because it is not directly connected to R2. So what R1 will do, R1 will tell R2 that Mr. R2, I know how to reach two networks. I can reach network 192.168.10.0. It is directly connected to me. I can also reach network 209.165.200.224. That one is also connected to me. I can show you how to reach them. So R2 will tell R1, thank you very much, R1. I can see you know how to reach two networks, but don't worry. I also know how to reach network 209.165.200.224. Why? Because I'm also directly connected to the same network. But thank you, I'm going to add network 192.168.10.0 in my routing table. And that's how R2 will add this remote network in its routing table. R2 does the same thing. R2 tells R1 that Mr. R1, I can show you how to reach network 10.1.2.0 and network 209.165.200.224 because they are directly connected to me. R1 says, thank you very much, R2, but don't worry. I also know how to reach the same network 209.165.200.224 because it's directly connected to me. But because of you, I'm going to add network 10.1.2.0. It was remote to me, but now I'm going to add it in my routing table so that I can reach it anytime that I want to reach it. Of course, we will talk more about dynamic routing when that time comes. When that time comes, I'm going to teach you about that. Now, we saw how to view or to display the routing table in a PC. How do we display the routing table in a router? The command is simple. Just need to say IP route, show IP route. That is to see the IPv4 routing table. To see the IPv6 routing table, you say show IPv6 route. So normally from IP to IPv6, from version 4 to version 6, when there's the word IP, replace it with IPv6. And you get to do that. And when you view the routing table, it's a very interesting one, which I will be teaching you how to read the routing table. The routing table, for one, it normally has a menu. It has a key here, which tells you the meaning of each and every letter that you will always see in the routing table. Okay? If it is L, local, C is connected, S is static, R is RIP, that's a dynamic routing protocol, M is mobile, B is BGP, border gateway protocol, D is EIGRP, I'll show you why, O is OSPF, okay, IA is OSPF inter area, and there's of course I should be IS here, so on and so forth. Okay, and then the routing table normally begins here, where it's written gateway of last resort. Sometimes it will say gateway of last resort is there, or sometimes it will not be there. The first column will always show you how the route was learned. Was it learned through a static route, S there? Was it learned through O for OSPF? Is it a directly connected network for both C and the L, or the C and L? We'll talk about much about this later on, but for now, I just want you to know that show IP route views the IPv4 routing table. Show IPv6 route view the IPv6 routing table. By the way, the show commands must be put at the privilege exec mode, not at the global. All show commands are put normally at the privilege exec mode. So the sum of those letters are actually here. L means directly connected. And by the way, just by assigning an IP address on an interface and activate that interface, C and L will always be recorded, where L will be the directly connected, the local interface, which is the IP address you had configured, but the C will be the network address where that IP belongs. S static, O OSPF, D EIGRP. Leave alone all this. This might not make a lot of sense now. Just contents of the routing table. That's what I can say for now. Now, I think this should mark the end of this class for today. Most of the things we have talked about there, we will actually talk about them. We'll talk about them much later in the next coming chapters. We will be able to discuss all of them. We'll be able to discuss all of them. So at this point in time, I'm going to welcome a few questions, if there are any. And if there are no questions, then I guess we'll be able to